Hello, I'm Ayngaran Thavanesan. Thank you very much for the fantastic opportunity to give this talk as part of the Quantum Cosmology seminar series. Today, I'd like to talk about how in this exciting era of precision cosmology, the observables imprinted across the night sky provide us with a powerful analytical handle on developing quantum theory of gravity for our universe, one of the central goals of quantum cosmology. When we look with our telescopes, we see light arriving from every direction in the sky. When we map this light, it forms what looks like a sphere of radiation surrounding us. This is the cosmic microwave background, or CMB. This light comes from the very earliest epoch of the universe that we can observe. It's essentially a baby picture of the universe, taken when it was only about 380,000 years old. At that time, during the final stages of the hot Big Bang, the universe was so hot and ionized that it was filled with light. The remarkable thing is that this light has traveled for more than 13 billion years to reach us, and although the CMB looks extremely uniform, it is not perfectly smooth. It contains tiny temperature fluctuations imprinted in the early universe. The colored spots you see in this picture represent these tiny variations in temperature across the sky. The colored spots we saw in the previous CMB map encode the very first seeds of cosmic structure. These tiny differences correspond to regions that were ever so slightly denser or less dense in the early universe. Over billions of years, they evolved into what we now call the cosmic web, the vast network of filaments, clusters, and voids that fills the universe. Gravity then amplified these small initial inhomogeneities, pulling matter together and gradually building up the large-scale structures we observe today, galaxies, clusters, and the enormous cosmic scaffolding that connects them. Now, these cosmological structures in the night sky are not randomly distributed. When we look at the universe on very large scales, we discover clear patterns. These patterns are encoded mathematically by cosmological correlators, statistical measures that tell us how different points in space are related. And we are currently in an era of precision cosmology where a whole suite of observational surveys has already produced incredibly detailed maps of both the early and the late universe, allowing us to measure these correlators with unprecedented accuracy. And what's even more exciting is that there is much more to come. The cosmological correlators we observe today ultimately trace back to physics in the very early universe, and the cosmic microwave background gives us our earliest direct snapshot through the tiny temperature and polarization variations that reflect the initial seeds of structure. But the CMB itself was produced hundreds of thousands of years after the earliest moments of the universe. So the real question is, what generated the primordial correlations long before the CMB formed? What mechanism before the hot Big Bang imprinted the patterns we see across the sky today? Well, it turns out that the early universe underwent an exponential expansion known as inflation, and the far future of the universe will undergo a similar exponential expansion driven by dark energy. During inflation, the rapid stretching of spacetime continuously produced extremely high energy particles. These particles left characteristic fingerprints on the primordial fluctuations, patterns that we can still observe today in the CMB and in the large-scale structure of the universe. Particle physicists study signatures from colliders to reconstruct high-energy events. As cosmologists, we can use the same logic to interpret inflation as a cosmological collider. The cosmological collider operated at energy scales above a million tera-electron volts, vastly beyond anything achievable on Earth, where even the LHC reaches only about 10 tera-electron volts. And the best part is, this collider has already run, and the data are written across the sky in the form of cosmological correlators. These correlators give us direct access to the era when quantum gravity shaped the universe. Using these ideas, we're now beginning to probe and constrain aspects of quantum gravity that would otherwise be completely inaccessible through experiments here on Earth. So how do we relate cosmology to the most fundamental levels of physics, in particular to a quantum theory of gravity? Well, some of the biggest conceptual breakthroughs in our understanding of quantum gravity have come from the holographic principle, which states that a theory of quantum gravity living in a volume of spacetime can be fully described by a non-gravitational quantum theory living on its boundary. A simple analogy is that the information about the contents of a can of soup is encoded on its surface. This idea is best realized in anti-de Sitter spacetime, in the well-known ADS-CFT correspondence. Here, a conformal field theory, quantum field theory with scale invariance, lives on the boundary. A Lorentzian CFT is dual to a Lorentzian ADS bulk, and if we Wick rotate, Euclidean ADS is dual to a Euclidean CFT. The correspondence works cleanly in either signature. However, anti-de Sitter space is not observed in nature, so this exact setup is not directly applicable to our universe. Since the universe we actually live in is not anti-de Sitter, ADS-CFT is not directly applicable. The very early universe, during inflation, and the very late universe, dominated by dark energy, both resemble de Sitter spacetime. Here, the story is very different. The expected holographic dual of Lorentzian de Sitter is a Euclidean CFT, but importantly, it is not obtained by Wick rotating a Lorentzian CFT. In contrast to ADS-CFT, where the emergent extra dimension is spatial, in holographic cosmology, the emergent dimension is time. This makes de Sitter holography, or holographic cosmology more broadly, far more subtle and less well understood than ADS-CFT. Holographic cosmology can be formulated in terms of the wave function of the universe, represented by the symbol psi in the diagram on the right, and also in the background behind me. During my PhD, I deliberately built expertise in cosmology and holography. I first studied the early universe's cosmological collider, then used those insights to advance a holographic description of de Sitter spacetime. This research not only probes gravity at its most fundamental level, but its predictions can also be tested observationally using the high-precision data from current and upcoming cosmological surveys. The wave function of the universe is a quantum state that encodes all of the information about the cosmological patterns we observe. It is the central object that tells us how likely different universes or different configurations of fields are. In my work on Cauchy slice holography, we showed that at finite time, the wave function is a partition function of a deformed Euclidean CFT. This makes the emergence of time as a dimension manifest. The Euclidean CFT is chosen so that it sits at the fixed point of a renormalization group flow. The crucial insight is that the RG scale in the boundary theory plays the role of time in the bulk. Moving along the RG flow corresponds precisely to evolving between Cauchy slices in the universe. This gives a concrete dynamical realization of holography for cosmology, where bulk Lorentzian time evolution emerges from RG flow in the dual Euclidean field theory. In holographic cosmology, the boundary Euclidean theory dual to the universe does not satisfy the usual properties of a standard Euclidean CFT. In particular, it violates reflection positivity, the constraint that unitary Lorentzian CFTs satisfy under Wick rotation. To systematically understand what constraints a holographic dual must satisfy, we developed a cosmological CPT theorem, which enabled us to show that the theory does satisfy another constraint known as reflection reality. The key idea is that three discrete symmetries form a closed group structure. Reflection reality, a generalization of reflection positivity implied by any theory with an indefinite norm. The 180 rotation, implied by Lorentz boosts in flat space or scalar invariance in cosmology. And finally, CRT, a combination of charge conjugation, reflection, time reversal, which is related to the familiar symmetry of CPT up to a rotation of spatial coordinates. This group structure allows us to make converse statements in both flat space and cosmology. By knowing any two of these symmetries, the third is automatically implied, with all three combining to give the identity. This general proof of the CPT theorem thus gives a systematic framework for identifying the non-perturbative constraints that a cosmological holographic dual must satisfy, even when reflection positivity fails. In holographic cosmology, the wave function of the universe is equivalent to the partition function of the boundary Euclidean theory, holographically dual to the universe, and can be parameterized into the form of a generating functional. The wave function can be computed semi-classically using a QFT and curved spacetime path integral. It is the overlap between a state in the infinite past, which we will assume to be the Bunch-Davies state, as well as the profile of some boundary field, which can in principle be any spinning field. The wave function coefficients are thus equivalent to the correlation functions of the holographic dual theory. This cosmological CPT theorem gives us a set of non-perturbative constraints on the Bunch-Davies wave function in FLRW cosmologies. These are constraints that the correlation functions of any cosmological holographic dual must satisfy. More specifically, the theorem allowed us to derive the exact constraint that bulk unitary time evolution imposes non-perturbatively, answering a long-standing question of how Lorentzian bulk time evolution non-perturbatively manifests itself and constrains the Euclidean boundary theory in holographic cosmology. Suppose we have a large N gauge theory, and that in the top limit, this theory is dual to closed strings on a cosmological background. So the cosmological analog of how SUN n equals 4 super Yang Mills is dual to string theory on ADS5 times S5. Consider, for example, the simplest non-planar four-loop ribbon graph with Euler characteristic 0 on the d-dimensional boundary. In the bulk, this corresponds to a closed string worldsheet torus diagram, i.e. a genus 1 surface in d+1 dimensions. Reflection reality, which is implied by bulk unitary time evolution, imposes a very strong constraint. Both n and the top coupling lambda must in general be complex, with a dimension-dependent phase. In particular, n is real only when the boundary dimension is odd, lambda is real only when the boundary dimension is even. So n and lambda cannot both be real simultaneously. This leads to a no-go theorem. Reflection positive large N gauge theories cannot be dual to unitary string cosmologies. Instead, holographic cosmology must involve more intrinsically complex configurations of string theory if it is to be genuinely stringy and consistent with bulk unitarity. Building on the cosmological CPT theorem and our exploration of non-unitary holographic duals, a number of promising research directions opens up. First, in the context of holographic large N gauge theories, such as N=4U super-Yang-Mills, which are quantum field theories with a large number of degrees of freedom, where the expansion in 1/n organizes quantum corrections, we showed that imposing our reflection reality constraint allowed us to identify a new class of complex large N gauge theories that are natural candidates for holographic duals of string quantum gravity on cosmological spacetimes. We refer to these as cosmic field theories. A key open question, though, is what are the explicit string backgrounds that correspond to these cosmic field theories? Second, finding UV completions of Cauchy cytolography. By applying these new constraints, we may be able to identify fully consistent ultraviolet completions of the relevantly deformed bulk CSH theory. Any such completion would automatically define a non-perturbative theory of bulk quantum gravity. This is particularly exciting because even in standard ADS-CFT, giving a complete non-perturbative bulk definition is still an outstanding challenge. Also, our generalization of the CPT theorem for flat space allows combo statements which opens several new research directions for even standard QFT, as in not QFT on curved spacetime. It gives a unified framework for studying non-reflection positive CFTs, such as the Li-Yang model, and more generally non-unitary PT-symmetric quantum field theories that arise in open quantum systems and experimental optics. This then lets us place these diverse theories within a single principled language rather than treating them as isolated exceptions. Secondly, it motivates deriving an analog of the Osterwalder-Schrader axioms, the usual conditions ensuring that a Euclidean field theory can be Wick rotated into a consistent unitary Lorentzian quantum theory. But now the idea is to build the corresponding axiomatic framework for theories obeying reflection reality and CRT instead of reflection positivity. The long-term goal is to establish a rigorous set of mathematical principles for studying these physically motivated but subtle non-unitary theories that appear in nature. Given the recent passing of Mar Vidanal on Thursday, 27th November, and as the first cosmologist of Elam Tamil descent, I would like to take this opportunity to dedicate my talk to the memory of my uncles, as well as countless other heroes who gave their lives resisting the genocide and ostracization of the Elam Tamil people by the Sri Lankan state. So overall, these directions illustrate how holographic cosmology, non-unitary field theory, and bulk quantum gravity can be systematically connected through the conceptual frameworks developed in our work. Thank you for listening.